Lesson 5, Algebraic Fractions. We're going to start off by recapping some concepts that you will have covered during your study of GCSE maths in relation to algebraic fractions. We will start by looking at how we can simplify algebraic fractions by making use of factorisation first. So we're going to simplify this algebraic fraction here. Now the crucial thing we must remember is to factorise both the numerator and denominator before we start trying to do any sort of cancellation. So our numerator factorises to give us x plus 2, x minus 2, it's a difference of two squares, and our denominator factorises to give us x plus 2, x plus 2. We can now divide the numerator and the denominator by a common factor of x plus 2, allowing this to cancel out, so to speak, and this leaves us with a final answer of x minus 2 over x plus 2. And you will remember from GCSE not to be tempted to do anything ridiculous like cancelling out the x's or cancelling out the 2's. Remember, this is x take away 2, one single factor, in x plus 2 another. We cannot cancel the x's through. So let's have a look at a second example. You can either try this yourself and then check the answer by pausing the video, or work through it as we look at it together. So we're going to factorise the numerator first. It's another difference of two squares. Always look out for these. 2x minus 5 multiplied by 2x plus 5. And then our denominator can also be factorised. We have 2x and x, and I think we're going to have a 5 here and a 1 here, and because we want a positive 3, we're going to have a negative 2 here and a positive 5 here. Now we can then see that we can divide through by 2x plus 5 and 2x plus 5 in the numerator and denominator, leaving us with 2x minus 5 in the numerator and x minus 1 in the denominator as a final answer. The brackets are optional, we don't need them at this point, but they may prevent you from doing something silly like cancelling out or trying to cross through the x's, which would be wrong. So let's have a look at an example involving multiplication. Again, factorising is going to be absolutely crucial here before we even consider simplifying. So let's start with the left-hand side. In the numerator, x squared minus 1 factorises to x plus 1, x subtract 1. And the denominator factorises to give us x plus 3, x plus 4, and we're multiplying by, in the numerator, x plus 3, x plus 3, and in the denominator we have x plus 1 and x plus 1. Now, what can we indeed cancel out? So we can cancel x plus 1 here, x plus 3 and one of the x plus 3's here, which means we're left with, in our numerator, x minus 1, x plus 3, and in our denominator, we're left with x plus 4, 2x plus 1. There is absolutely no need to expand the brackets in either the numerator or the denominator at this point, unless you're asked to do so, and expressions are usually more helpful to us if they're in a factorised format, if, for example, we're trying to solve an equation of some sort. So let's have a look at a division question. Now, you will recall this from when you've looked at dividing numerical fractions as well. We will keep the first fraction as it is. We need to take the reciprocal of the second fraction, which some people like to describe as flipping the fraction. So as you can see, the numerator becomes the denominator and vice versa. And of course, we're now multiplying rather than dividing. So crucially, we need to factorise each of these quadratics very carefully. Spot a difference of 2 squares in the denominator of the left-hand fraction again. And we'll just draw in these parts of the fraction as well. Now, are there any factors which can cancel through? So here, an x plus 3 and an x plus 3, and we have an x minus 5 and an x minus 5. So this leaves us with our final answer, x minus 4, 3x plus, I think there should be a 1 here, 3x plus 1, all over x plus 5, x minus 2. And again, no need to expand the brackets in the numerator and denominator unless we are really instructed to do so. So we're going to have a look at adding and subtracting fractions, algebraic fractions. Crucial that the fractions have a common denominator. So here in this first example, the common denominator is going to be x and 2x minus 1 as a product. So each of the fractions will need to be adapted. In the first example, we have a 4, and the denominator has been multiplied by 2x minus 1, which means that we need to do the same to the numerator. So I'll write it as 4 bracket 2x minus 1 for the moment. And in the second fraction, the denominator has been multiplied by x, which means the numerator has to be multiplied by x as well. So we have this result here. Now, adding the two fractions together, now that they have the same common denominator, we can add the numerators and the whole thing will be over a denominator of x bracket 2x minus 1. So simplifying the terms in the numerator, this will give us 8x minus 4 plus 3x. So the final answer will be 11x minus 4 over a denominator of x bracket 2x minus 1. Again, no need to expand the denominator unless we are instructed to do so. Now, quite often we jump straight from this step directly to this step, missing out the one beforehand. You will see people talking about cross-multiplying, the idea being that it looks like you do something like this. So the 4 multiplies by the 2x minus 1, which gives you this part here, the 8x minus 4. And the x multiplies up by the 3 here, which gives you the 3x, and then you just combine the denominators. That is another way of thinking about it, but the actual process is what has occurred here. If you want to jump directly to this step here, that's absolutely fine, as long as you understand the mathematics behind this. Let's take a look at another example here. On the right-hand side, we're going to add together 2 over x plus 3 and 5 over x minus 1. This time we'll use the concept of cross-multiplication just as a shortcut, now that we've seen where this actually comes from. So that will involve changes here and here. So we end up with 2 being multiplied by x minus 1, plus 5 multiplied by x plus 3, and all over a common denominator, which is a product of x plus 3 and x minus 1. We're then going to simplify the numerator, which will give us 7x plus 13 when fully simplified. This is all over a denominator of x plus 3 x minus 1, which again we are not going to expand unnecessarily. Let's have a look at a third example. I've got 3y over x minus 5 over x squared. Now stop and think about this for a moment, because there's a common misconception here that the common denominator should be x cubed, that you always multiply the original denominators together without thinking about it further. But actually, we should really try and find the lowest common denominator possible, in which case that denominator would be x squared. So we would multiply this by x here and this by x here, so this first fraction becomes 3xy over x squared. The second fraction remains as it is, 5 over x squared, and there's absolutely no need to have a denominator of x cubed. You now have a common denominator, x squared. The numerator can be expressed 3xy minus 5, and we are done. Now in theory, if you had taken a denominator of x cubed as a common denominator, you would have had an extra factor of x to cancel at the very end, so it would have just involved one further step of working. We do want to try and aim to be as efficient as possible, so we look for our lowest common denominator. So let's have a look at a fourth example. You may wish to have a go at this yourself, so pause the video and try it and then check your answer, or work it through along with me. So again, I'm going to use the shortcut, thinking of this as cross multiplication. So this gives me 10x multiplied by x plus 1 minus 3 bracket 2x minus 1. Please make sure you keep all of the brackets in place carefully, especially when a subtraction is involved and negatives are in view. Here's our denominator, and now we're going to simplify the numerator carefully, which will give us 10x squared plus 4x plus 3, and this is over a denominator of 2x minus 1, x plus 1. Always be careful, because there is a possibility that your numerator might factorise further. It doesn't in this case, but do always check, just in case further simplification could be carried out. So let's have a look at one final example in which we have to do a little bit of simplification before we can do the subtraction. So in each of these cases, the denominator needs to be factorised, ideally, before we look at finding a common denominator. We could, in theory, make a common denominator of these two quadratics, but it might not be the lowest common denominator, in which case we create more work for ourselves. So on the left-hand side, we can factorise the denominator as this, and on the right-hand side, we can factorise the denominator as this. Now, hopefully we can see that both of these have a common factor of x plus 1, which means that we can create an overall common denominator which consists of an x plus 1, an x minus 2, and another x plus 1. We do need to include x plus 1 twice, because if you look at the denominator of the fraction on the left-hand side, it includes x plus 1 twice. So this is our lowest common denominator. Now, the fraction on the left-hand side is gaining an x minus 2, so we must multiply by x minus 2 in both the numerator and the denominator, and on the right-hand side we are gaining an additional x plus 1 here and here. So this means that we have 2x minus 2, and then subtract a single x plus 1. So our final answer is going to be x minus 5 all over x plus 1, x minus 2, x plus 1. So we're going to spend a little time discussing proper and improper fractions and what these mean in the context of algebraic fractions. So let's start with defining a proper algebraic fraction. To be a proper algebraic fraction, the order, which is the highest power of a term in the numerator, is less than the order of the denominator. Let's look at some examples to try and illustrate this. So an example could be something like 5x plus 3 over 2x squared minus 1. Now the order of the numerator is 1 because that's the highest power of any x term in the numerator. The order of the denominator is 2 because that's the highest power of any x term in the denominator. So we can see that the order of the numerator is less than the order of the denominator. Let's list a few other examples as well. So for instance, 2 over 1 minus x, the order of the numerator here is 0 and the order of the denominator here is 1. And let's list one final example, 4x over x plus 3 x plus 1. Now the order of the numerator is 1 and the order of the denominator is 2, even though we haven't yet expanded the brackets. Once we do that, we'll be able to see very clearly the x squared term, giving the denominator an order of 2. Now the opposite is true of an improper fraction, an improper algebraic fraction. So this is probably best illustrated with some examples. So for instance, 2x over x plus 1. Now, what's the order in both of the numerator and the denominator here? Well, the order in the numerator is 1, and the order in the denominator is also 1. So the numerator and denominator have the same order, which means it can't be a proper algebraic fraction if you look at the original definition. Let's write down another example. X squared over x minus 2, and we can see again the order in the numerator is 2, which is higher than the order in the denominator. Let's look at an example. So we have here a very definite improper algebraic fraction. The order of the numerator is 3 because that's the highest power of an x term in the numerator, and the order of the denominator is 1. So it's definitely an improper algebraic fraction. So if we're asked to simplify this, there are different ways in which we could do this. I'm going to choose to do some polynomial division. So this will be a good opportunity to refresh our memory of polynomial division. I'm going to start off by considering x and x cubed. Now, what do we multiply x by to create x cubed? We multiply it by x squared. So x squared, if we multiply back, gives us x cubed plus 2x squared. So subtract, and let's draw a line in like this. So doing our subtraction, well, both of the first terms cancel out, leaving us with minus 6x minus 12. So this then gives us minus 6 here, because that's what we multiply x by to create minus 6x here. Multiply back again, so that gives us minus 6x minus 12. So subtracting gives us an answer of 0. So there's 0 remainder here. So the answer simply is x squared minus 6. So let's explore improper fractions in a little bit more detail. We're going to consider the improper fraction x minus 3 over x plus 2, and we're going to write it in the form a plus b over x plus 2. Now I'm going to look at doing this using two slightly different methods. So method 1, I'm going to take x minus 3 over x plus 2, and I'm going to leave the denominator alone as x plus 2, but I'm going to rewrite the numerator as x plus 2 minus 5. Now have a look at that. There's nothing wrong with this because x add 2 minus 5 in yellow is x minus 3. So it is still the same numerator, I've just adjusted it slightly. So now, if I think about this part separately, I can divide each part of this by x plus 2. So I have x plus 2 over x plus 2, subtract 5 over x plus 2, which of course gives me 1, take away 5 over x plus 2. And I've written the original improper fraction in this format over here. Now, let's look at an alternative method in which we could have done this, which is to say we could have used some polynomial division again. So this time, remember the numerator, x minus 3, is being divided by the denominator x plus 2. So what do we multiply x by to create x? 1. Multiply back, so we have x plus 2, and then subtract. This gives me minus 5. Now, of course, that's then a remainder. So that tells me that x minus 2 over x plus 2 must be equal to 1. And then we have a remainder, minus 5, which has not yet been divided by this x plus 2. So we get to the same answer using algebraic division. So, what was the purpose of us rewriting the original expression in this new format? Well, we're going to use this to sketch the graph of y equals 1 minus 5 over x plus 2 using a series of transformations of y equals 1 over x. So, here are the different stages that I'm going to work with. I'm going to say f of x is equal to 1 over x, which is our starting point. Now, I'm then going to think about the denominator here, so that's 1 over x plus 2, which of course means we must be thinking about f of x plus 2. So slowly and steadily, we're building up this function here. So what could be the next stage? Well, what about the 5 in the numerator? 5 over x plus 2. So this, of course, is 5fx plus 2. And so on and so forth as we build up. What have we got next? So we now have a negative. So that's negative 5x plus 2. So that's negative 5f bracket x plus 2. And then we have our final, which is to add a 1. And I'm going to specifically write it like this because I think it's slightly easier to understand the significance of the plus 1 at the end. And we can see that this is minus 5f x plus 2 add a 1 at the end. So what are the different transformations that have taken place? Let's list them. So first of all, we've of course started with f of x equals 1 over x. Now the first transformation over here, f bracket x plus 2, is of course a translation. So this is a good opportunity to recap our knowledge of transformations. So this is a translation with a vector negative 2, 0. Now what about this next one? The multiplication by 5. This of course is a stretch, which is parallel to or in the direction of the y-axis and has a scale factor equal to 5. Now the blue transformation, the negative, this is a reflection in the x-axis. And then we have one final step here, the addition of the 1, which is a final translation involving a vector 0, 1. So let's take a look at the stages of sketching the final graph using the concept of graph transformations. Of course, you can follow this through using your graphical calculator as well. Let's have a look at the first step. So we're going to sketch a quick graph of y equals 1 over x. So this, of course, looks like this. Just carefully showing our approach to the coordinate axes, which are currently asymptotes. Now, second stage, we translate with a vector -2, 0, which of course means we now have a vertical asymptote, which instead of being the y-axis is the line x equals -2. And the graph now looks like this. The x-axis remains an asymptote. We now have a y-intercept, which we can work out by substituting x equals 0 into the function, which gives us 0.5. Right, the next transformation, we have a stretch in the y direction with a scale factor of 5. This does not affect the asymptote at x equals -2, and the horizontal asymptote, which is the x-axis, also remains in place. Any y-coordinate is multiplied by 5, any x-coordinate remains the same, so we now have a y-intercept of 0, 5 over 2. None of this is to scale, by the way. So all the y-coordinates basically become stretched. The x-coordinate is still an asymptote, and we still have a portion of the graph here as well. Now, in the next stage, we have a reflection in the x-axis. So we still have this vertical asymptote at x equals -2, but our previous y-intercept will become 0, -5 over 2 like this, and we have our graph here, and here the x-axis remains an asymptote as well. Now in the last sketch, we translate with a vector 0, 1, so the vertical asymptote, x equals -2, is still in place, but we now have a horizontal asymptote at x equals 1 rather than at the x-axis. Now, all the y-coordinates will be increased by a value of 1, so we now have a y-intercept of 0, -3 over 2. There we have this portion of the graph. Like that, and then we have the other portion of the graph up over here. We also now have an x-intercept, which you can work out by making y equal to 0. So this gives you an equation, very simple equation that you can solve, and if you rearrange this, you will find that x plus 2 is equal to 5, x is therefore equal to 3, so this root here is 3, 0. And this concludes our series of graph sketches. Now, of course, you may be wondering, what is the value of doing that? Well, if we didn't have a graphical calculator or graphing software to hand, by rewriting our improper fraction in a different format as 1 minus 5 over x plus 2, we were able to make use of our knowledge of graph transformations to be able to sketch what would be perhaps a more complex graph to sketch if we were doing it otherwise, by hand.